Good evening. This is CIS 496K assignment 2 about image filtering. In the first question, I took the derivative filter and since I'm supposed to be performing convolution, I flipped it and I then ran it over this grid and it got me the final values. And I did this on paper, so I'll be submitting question 1 and question 2 on paper. Then it told me to compute the gradients at pixels, these ones. And the way I did this was I found the gradient in the x direction and the gradient in the y direction. And I used the formula gradient in x squared plus gradient in y squared. And I take the square root of that to find the magnitude. And then the third question was to write a convolution function and then pad the image with zeros based on the kernel. And then, of course, appropriately flip the input kernel because it's convolution. That's what I did right here. This is the function. It flips the filter here. And then it pads the image based on the filter, whether it's a 3x3, a 5x5, blah, blah, blah. And it declares an output image. Right now, it's just zeros. It performs a convolution and it assigns the output values to that output image. And at the end, it returns the output image after normalizing it between 0 and 255. Then the fourth question was to perform convolution using a built-in and mine with this Gaussian kernel and see if there's any difference. So I'll just run my code now and we'll see. So this was based on mine, and then this image was from the second image is like from the inbuilt one, and this is the difference. As you can see, like there is a very minute difference, and if I check it in the print function, there's a difference of 0.0076, which is very close to zero, and the output is almost a pitch black screen, so there is almost no difference. And the last question required me to convolve with a 2D Gaussian and then with two separate 1D Gaussians and see the difference, like to see what I observe. And right here, that's what I did. So I took in an image, 1.4, no, here. I took in a 640 by 480 image. I performed convolution first using a 2D, and then I performed convolution using a 1D, and then I printed out the execution times for both. And right here, you can see that the 2D is 0.022, and this is 0.006. So you can see that the 1D separable are fast in the 2D Gaussians. However, since these are both really fast, the computer's hardware is a major factor in the output times that I'm seeing. But you can still see the 2D takes more time than the separable 1D Gaussians. Then the next question was about comparing convolution, spatial, and frequency domain. And so I had to first perform convolution using all these filters in spatial and then the same filters in frequency and then plot them. And I'll come here and then the code is still running. So it's now convolving them based in the filter, frequency domain and the spatial domain. And I should have a graph very soon. And there we go, that's the graph. So what we can see here is that the frequency domain's time is usually like kind of constant, and it's much faster than a spatial convolution as the filter size increases. And that is what I've also outputted here, that uh, right here. So this is where that this plot shows the spatial convolution execution time increases significantly with larger kernel sizes, while frequency domain convolution remains almost constant. And this highlights that the frequency-based convolution is much more efficient for large kernels, making it a better choice when processing large filters. So I'll just close that. And then the last question required me to phase swap. So select two images with the same dimensions and then swap the phases between them and then describe the final images. And the images that we just saw, the four images, put them back on the screen. You can see here, okay. You can see here that the phase from this one was now put into this one, and the phase from this one was now put into this one. And after swapping, you can see that this is noisy and a bit more blurry as compared to the original images. And that is what I said. The person image with city face is a blurry version of the person with city-like textures or patterns. And a city image with person face is a distorted version of the city with facial features or edges imposed. So what I learned from this assignment was about like image filtering and in spatial and frequency domain. And I got to apply it practically. Thank you.